Let's continue in section 3.6 and let's look at rational inequalities. In the previous video, we looked at solving a polynomial inequality. Let's start with the definition of a rational inequality. A rational inequality is any inequality that can be put into one of the forms f of x less than 0, f of x greater than 0, f of x less than or equal to 0, or f of x greater than or equal to 0, where f is a rational function. So this is our definition of a rational inequality. So we want to look at our procedure for solving these types of inequalities. So our first step is to express the inequality so that one side is 0. Most people do best if the right side is 0, and the other side is a single quotient. When we say side, we mean the right side of the inequality symbol has a 0 on it, and the left side of the inequality symbol is a single quotient. Our next step is to set the numerator and the denominator of the rational function equal to 0. Third, we want to locate the boundary points on a number line and separate the line into intervals. So any real numbers that we get from step 2 are our boundary points. In our fourth step, we're going to choose one test value within each interval and evaluate our function at that number. This test value is going to represent all the numbers in the interval. Fifth, we're going to write the solution set based upon the true results from step 4. So let's apply these steps to exercise 70 from our section 3.6. Okay, so remember our second step is that we're going to set the numerator and the denominator equal to 0. So our numerator is x squared minus 3x plus 2 equals 0. So any real solutions that we get from here are going to be boundary points. And we also need to take and set our denominator equal to 0. In this case, our denominator is x squared minus 2x minus 3, and we set that equal to 0. So we're going to attempt to solve these by factoring, if at all possible. So this equation on the left factors into the quantity x minus 1 times the quantity x minus 2. So that equals 0. And the only way that is going to yield 0 is if x minus 1 is 0 or if x minus 2 is 0. And this would mean x is 1 or x is 2. So these solutions are possibilities, are my boundary points that I'm going to use to divide up the number line. Let's solve this equation, which factors into x minus 3 times x plus 1. And that's set equal to 0. And of course, that'll only happen. This product will be 0 if either x minus 3 is 0 or the other factor, x plus 1, is 0. When I solve these, I find that x either needs to be 3 or x needs to be negative 1. So I have 4 boundary points. I always wind up with the number line having one more interval than I have boundary points. So before, in the previous example, we had one boundary point, so the number line was divided up into two intervals. Here we have 3 boundary points, so the number line is divided up into, we have 4 boundary points, I'm sorry. The number line is divided up into 5 intervals then. So anything left of -1 forms an interval. Anything between -1 and 1 forms an interval. Anything between 1 and 2 forms an interval. Anything between 2 and 3 forms an interval. And anything to the right of 3 forms an interval. So those are my 5 intervals. So I want to pick a test number in each one of these intervals to represent all the numbers on the interval. So in this leftmost interval, I'm going to pick x equal to -2. You can pick any value smaller than 1. Here I'm going to put x equal to 0. Here I'm going to use x equal to 1.5. Here I'm going to use x equal to 2.5. And here x is equal to 4. And those are my test numbers. And I'm going to actually test my function at those values. The easiest form for me to put the function in is to put it in factored form. Okay, so we've got our 5 intervals. We've got our test numbers, x equal -2, x equals 0, x equal 1.5, x equal to 2.5, and x equal to 4. So those are our test numbers. And again, you want to make sure that those numbers actually lie in the intervals. Okay, so what we're testing is x minus 1. We're going to put it in factored form. We're going to test x minus 1 times x minus 2 over x minus 3 times x plus 1. And that needs to be greater than 0. So that's what we're testing. We're going to take each one of the test numbers and place them into that expression. So -2 minus 1 is -3. -2 minus 2 is -4. -2 minus 3 is -5. And -2 plus 1 is -1. So we replace every x with -2. Okay, so I've typed these in to save space. And what we're doing in each case is we're going in and we're replacing our x with our test number. So that's what we're doing in each case, replacing x with our test number. So here are in our leftmost interval, our test number is -2. So we're replacing all x's with negative 2. And let's evaluate that. So we wind up with negative 3 times negative 4 times negative 5 times negative 1. So we wind up with a positive over a positive. Okay, so in this first interval, we wind up with 2 greater than 0 when we make all of our substitutions. And that is actually true. 2 is greater than 0. So all the numbers in our first interval make our inequality true. So our leftmost interval there is one that makes all of our all numbers smaller than negative 1 make the inequality true. So let's follow suit, and now let's replace all of the x values in the inequality with 0. Okay, so for our second test number, our second test number is 0. We have replaced all of the x's in the inequality with 0. So okay, so now we've replaced all x's with 1.5 as we're in this next interval. So we've replaced all x's with 1.5, and we wind up with 0.5 times negative 0.5 over negative 1.5 times 2.5. The point here, we can do the calculations. We'll actually get 1 over 15 here. But what really matters is the sign. So we got a negative. This product in the numerator will be negative. The product in the denominator will be negative. So a negative divided by a negative is positive. And that's what really matters here, is the sign of what we wind up with. So we wind up with a positive greater than 0. And our only concern is, once we know the sign of that, our only concern is that true? Is a positive number bigger than 0? And of course that is true. So this is true. And we continue down the line, replacing the test number. Our next test number is 2.5. So we replace all x's with 2.5. And so we wind up with a positive in the numerator over a negative in the denominator. So a positive divided by a negative is negative. And so our question boils down to, is a negative number bigger than 0? And we know, of course, that that's false. And then the last result, the last interval, we're replacing all x's with 4. So we replace all x's with 4. And we wind up with 3 times 2 over 1 times 5. Obviously, that's a positive number. And of course, that is greater than 0. A shortcut that you can use if you're sure that your work in the first interval is correct, and if your expression contains factors that are all raised to odd powers, then the signs are going to always alternate. So the true falses are always going to alternate. If the so notice x minus 1 is raised to the first power. X minus 2 is raised to the first power. So is x minus 3. So is x plus 1. So the power on all of these factors is odd. If that's true, if the power on all factors in your expression that gives you your rational function, if those powers are odd, then once you find out whether the test number makes the statement true in the very first interval, the next interval is going to be made false by the test number for that interval, so forth and so on. So as long as the powers on your factors are odd, these are going to alternate. So once you get a true interval, the next interval is going to be false. Where you have to be careful with using that shortcut is if there are any even powers on any of your factors in your factored rational expression, then that may not be true. So you do have to know when you can use that shortcut. Anyway, we went the long route this time with this, and we see where the inequality is true and on what intervals it is false. So I've written down the intervals where the test value made the inequality true. So the union of these intervals is actually my solution set. So my solution set is equal to all of the numbers smaller than -1, unite it with all of the numbers between 1 and 2, unite it with all of the numbers greater than 3. So this is my solution set for this inequality. Now I want to look at what would happen if we were solving a slightly different inequality. Let's graph that solution set as well. So here's our number line, and let's actually show these intervals that make up our solution set. So we can have any number less than -1. So we shade that region. Any number between 1 and 2. So we put the appropriate symbol above. These are all going to be parentheses. And any number bigger than 3. So there is our solution set as a graph, as a number line graph. And notice I do need to show the endpoints on that. I want to look at solving, using what we've done and solving a slightly different inequality. We're going to use this information that we've obtained to solve this inequality. Okay, so our solution set is all the numbers smaller than -1, unite it with all the numbers between 1 and 2, unite it with all the numbers bigger than 3. So that's the solution set for this inequality, okay, which is our original inequality in factored form. So the only change I want to make here is to change this from this rational function greater than 0 to this rational function greater than or equal to 0. And I want to look at how that changes our result. Now, in the polynomial function, polynomial inequality, if our inequality changed from a greater than to a greater than or equal to, the only change that would occur is that all the boundary points would be included now. But with a rational inequality, the case is slightly different. What has to happen now is that only the boundary points that made the numerator 0 are included. And remember, that was x equal to 1 and x equal to 2. So we only include those boundary points. We still omit the boundary points that made the denominator 0. That would be x equal to 3 and x equal to -1. Because we cannot divide by 0. That's always undefined. So in the case of a rational inequality, when my symbol changes from a greater than to a greater than or equal to, I only include the boundary points that make the numerator 0. So let's look at the solution set for this. All right, so I still have all numbers less than -1, but now I unite that with all numbers between 1 and 2, including 1 and 2. And those two intervals get united with all numbers bigger than 3. So notice this is my solution set for this rational function greater than or equal to 0. I omit the -1 and the 3 still as part of the solution set because they make the expression undefined. But I include the 1 and the 2 because they make the numerator 0, which makes the overall function 0. And I also still include all the numbers between 1 and 2.